Welcome back to FFBMD. Name is fact, but material is denied. Work. Now today I am going to discuss about the work. Whenever a force is applied on the body and body is displaced, then in language of physics it is said that work is happening. Definition of work. It is defined as the product of magnitude of displacement and the component of force in the direction of displacement. Let us consider a block is placed at the ground and a force is acting at angle theta with the horizontal, and that force is a F vector. Due to influence of this force, body displaces horizontally, traveling a distance s in some time interval. In this time interval, we have to calculate the work done by this force. So from the definition, we know that work is defined as the distance, displacement multiplied by component of force along the displacement. Here displacement is s, magnitude of displacement is s multiplied by, and the component of force is f cos theta. So we have multiplied f cos theta, which comes out to be fs cos theta. Now this can be written as dot product f vector dot s vector. Thus work is the dot product of force vector and displacement vector. Now we can discuss different case or situation. One, when f vector and s vector are along the same direction. When f vector and s vector are along the same direction, that is theta equals to 0 degree. Theta equals to 0 degree. Then we have here the situation is shown. Force is applied in this direction and also displacement is being in this direction. So we can write W equals to f vector dot s vector fs cos theta equals to fs into cos 0 equals to fs. So the work will be f into s in this case. Now the case 2, when f vector and s vector are along opposite direction, that is theta equals to 180 degree. That is, we are applying force on the force is acting in this direction, but body is moving in this direction and travels a distance s. In this case, work will be f vector dot s vector fs cos theta fs cos 180 degrees, since theta equals to 180 equals to minus f into s, negative work. That is, if body is moving, the force is acting opposite to the movement, then work will be negative. Here in this figure a situation is shown where kinetic friction is acting opposite to the movement of body. So work done by kinetic friction will be negative and given by minus f into s. This is also the shown for the case of a where kinetic friction is acting on the body, because we know that kinetic friction is acting opposite to the movement of body. So in this case work will be negative and given by minus mu k into mg into s, where s is the displacement. Case 3, when f vector and s vector are perpendicular to each other, that is force and displacement are perpendicular to each other. In this case, W equals to f vector dot s vector equals to fs cos theta equals to fs cos 90 degree equals to fs into 0 equals to 0. In this case, when force and displacement are perpendicular to each other, the work done by that force will be 0. Question. Here a block is placed on the table and mass of block is 5 kg. A force is applied on this horizontally and This block covers a distance of 5 meters along the applied force. Then find A. Work done by the applied force, work done by the friction force, work done by the gravity, and work done by normal force. And the kinetic friction between block surface and table surface is given 0.1. Also we have to take G equals to 10 meter per second square. Solution 1. Work done by applied force applied dot S vector, displacement vector, which is equals to F applied S cos 0, because both are in same direction. So F applied into S. The value of F applied is 10 Newton and the magnitude of displacement is 5 meter. So we get 50 joule of work done by the applied force. Case second, work done by frictional force. Because friction force is acting in the opposite direction of the movement of the body, so there is the value of theta is 180 degree. So we can write work done by frictional force equals to frictional force vector dot S vector, or Fk dot S cos 180 degree, because angle between frictional force and displacement vector is theta, is 180. So this equals to minus Fk into S. Now we have Fk is equal to μk into mg. So putting this value, we get minus μk mgs. Now use all value, we get minus 25 joule answer. So work done by frictional force is negative. Again, now third, work done by normal force. From the free body diagram, we see that normal force is acting perpendicular to the surface, and in this case displacement and normal force make 90 degree angle. So we can write the work done by normal force Wn equals to F dot S equal to N dot S equals to Ns cos 90 degree equals to 0. So normal work done by normal force will be equal to 0. Similarly, we can calculate work done by gravity. This gravitational force, that is weight, also work perpendicular to the displacement. So we can write F dot S equals to mg dot S equals to mg S cos 90 equals to 0. Now work done by a variable force. In the above example, we have considered that force is constant during the motion. But what will happen when the force is variable during the motion? Here the situation is shown. For example, during the x1 displacement, force acting on body is Fx1. During the Fx2 displacement, force acting on the body is Fx2 and Fx3, similarly so on. Then in this case, what will be the work done by the variable force? To solve this problem, let's consider. In this case, force is variable and is a function of x. That is, function of x means with displacement, force is also changing. For an infinitely small displacement, force may be considered as a constant. So work done in displacing the particle by a small displacement, dw equals to fx dot dx or ff vector dot dx vector. The situation is shown in this figure. We are taking an infinitely small displacement, and we can consider during this displacement force is constant. And so and that time the force acting on the body is fx vector. So we can calculate the work done by infinitesimal work will be equal to fx dot dx vector. Now since f and ds are in same direction, so theta equals to 0 degree. So total work done in displacing the particle from xi to xf is w equals to integration xi to xf dw equals to xi to xf fx dot dx, where xi is the initial displacement and xf is the final displacement. We have taken the limit. and this can be written as in vector form. W equals to Ri vector to R integration Ri vector to Rf vector Fr vector dot dr vector, where force is the in this case force is the function of displacement. Now graphical method. Here a graph between force and displacement is drawn. Consider a body under the action of variable force Fx is displaced from initial position xi to final position xf along the direction of force. The force displacement graph is shown in figure. At xi, when the displacement is xi, the force acting on the body is fxi, and when the displacement is xf, the force acting on the body is fxf. Now consider a point A. A small displacement delta x. During this, the force can be considered as constant and it is given by fx. Now we know that the displacement force graph is shown in the figure. Divide total displacement into a large number of a small displacement with delta x. The force fx may be considered constant over that interval. Let fx is the average value of fx within the interval delta x. Then work done is delta w equals to average fx into delta x, equation 1. From graph, average x into delta x is equal to area of a strip ABCD. Hence work done, average of fx dx equals to area of a strip of width delta x. Now the total work done by the force when the body is displaced from xi to xf is given by w equals to sigma delta w equal to sigma fx average fx into delta x, that is equals to area of all strip between xi and xf. Taking limit delta x tends to 0, w equals to limit delta x tends to 0 sigma delta w, limit delta x tends to 0 sigma average fx into delta x equals to integration of xi to xf fx dx equals to area under the curve between xi and xf. Example, an object is displaced from r1 vector 2i cap plus 3j cap meter to r2 vector 4i cap plus 6j cap meter under a force F vector equals to 3x square I cap plus 2ij cap newton. Find the work done by this force. Solution. We have formula of work done. xi to r1 integration w equals to r1 to r2 f vector dot dr vector. This implies w equals to r1 vector to r2 vector. We have f vector given as 3x square I cap plus 2ij cap dot dx I cap plus dyj cap. Taking dot product, we have integration r1 to r2 3x square dx plus 2y dy, or this can be written as integration r1 to r2 3x square dx plus r1 to r2 2y dy equals to 3 into, because 3 is constant so it comes out of the integration. Now we have initial, because here function is x, so we have to take the value of in the limit we have to take the value of x. So initial value of x is 2 and final value of x is 4 and x square dx. Similarly we can write integration y equals to 3 to y equals to 6 y dy. Solving this, we have 3 into x square by 3 limit 2 to 4 plus 2 into y square by 2 limit 2 to 4, and finally get the value of the work done equals to 68 joule. Answer. Let's another example. Here a body is displaced on horizontal surface with applying force of 100 Newton. It moves with it moves and travels a distance of 10 meter at point B. Now from point B the applied force changes to, and now point B to C, the applied force changes linearly from 100 Newton to 15 Newton. Then find the value applied force decreases linearly from 100 Newton at B to 50 Newton at C. The frictional force acting on the trunk throughout is 50 Newton. A. Draw the graph between 1. Applied forces versus displacement, 2. Friction force versus displacement. B. Calculate the work done by the both forces. Here the graph is shown in the figure. Because friction force is always acting in the negative opposite to the motion, so it is negative and its value is fixed 50 Newton. Now from B to C, here shown a force of 100 Newton is acting, so this line will showing the 100 Newton, and from C to E traveling 10 meter, the force change from 100 Newton to 50 Newton, so this line shows the motion from B to C. Now we can calculate work done by the applied force. Equals WF equals to area of figure ABCEIDA equals to area of rectangle ABCD plus area of trapezium CEID. Putting all value we get 1750 joule answer. Now work done by the frictional force, area of figure GHIO minus 50 into 20 minus 100 joule answer.